One further issue I'd like to address with respect to carbonyls and introducing carbonyls is just where carbonyls come from synthetically. We access the major forms of carbonyls, which are ketones, aldehydes, and carboxylic acids, by the oxidation of alcohols. Oxidation is a process in which a molecule formally loses electrons, and in the case of, for example, oxidation of an alcohol to a ketone, we see that we're going to lose two different hydrogen atoms from our molecule. Each of those hydrogen atoms will take away one electron. Formally we're losing H2, and the remaining electrons, one on oxygen and one on carbon, will come together to form a new pi bond. We're not going to go too in-depth into the mechanism of this process or how it happens. We will look at it briefly on the next slide. But what I'd like you to be familiar with is just what oxidizing reagents we commonly use for what purpose in order to achieve which functional group. The ketone is the easiest to access and the least fiddly. If you start with a secondary alcohol, there's precisely one hydrogen on the oxygen-bearing carbon that can lose a hydrogen and form a double bond to oxygen and form a ketone. There is no other option in this case. So a secondary alcohol will become a ketone. The oxidizing agents we use for all of these transformations contain high valent or high oxidation state chromium. If we wish to oxidize a secondary alcohol to a ketone, then we can use pyridinium chlorochromate, or PCC, which is a derivative of chromic acid. Or we can just use chromic acid, which may be presented as chromic acid H2CrO4, or is sometimes used in the lab as the potassium salt of dichromate, Cr2O7, with acid in water. Chromic acid is done in aqueous solvents. PCC can be used in non-water type solvents. Either of these will give a ketone. Why do we have different oxidizing reagents? Well, if we try to oxidize a primary alcohol, there are two protons that could be lost from the carbon, and we could have potentially two oxidation steps occur. If we would like to only do one and turn that primary alcohol into an aldehyde, we must use PCC or a relative PDC. These are just two very closely related oxidizing reagents. Either one of them is perfectly adequate. PCC is just fine to remember. PCC stops with the primary alcohol at the aldehyde oxidation state. If we use chromic acid instead, we will take that primary alcohol all the way up through two oxidation steps up to the carboxylic acid. So this is why we introduce two different oxidizing reagents. In the case of the secondary alcohol, either of them will take it to the ketone. That's as far as things can go with the oxidation of the secondary alcohol. The primary alcohol is more sensitive. Depending on the reagent we choose, PCC will take it to the aldehyde, or chromic acid in water will take it all the way to the carboxylic acid. From here, from the carboxylic acid, we can then go on to access carboxylic acid derivatives such as esters and amides and other derivatives of the carboxylic acid, and we will see that in a future lesson. A brief overview of the mechanism by which this high valent chromium is able to oxidize an alcohol. If we look at the alcohol and the structure of chromic acid, what we find is that when these are reacted with one another in acidic solution, that the oxygen in the alcohol attacks the highly oxidized, very positively charged chromium atom in the chromic acid to form what we call a chromate ester. And that chromate ester, again, this chromium is very highly oxidized, very highly positively charged, is pulling on electrons very strongly, and would like to get more electrons and become reduced. Remember from general chemistry, oxidizing agents oxidize other molecules and in the process are reduced. They gain electrons. The chromate ester decomposes by a beta elimination. This is a kind of reaction that we've seen before. Essentially, this chromium is now a good leaving group, could accept electrons onto itself to be reduced. A weak base such as water can grab a proton off of our alcohol, and those electrons from the proton abstraction will push into the sigma star of the oxygen-chromium bond, forming a new pi bond between carbon and oxygen and pushing out the electrons from the oxygen-chromium bond onto chromium. That gives us this reduced chromium species and the oxidized carbonyl on our organic molecule. And then, not to worry about it too much, this chromium is further decomposed by some further redox reactions and ends up in the +3 state. It started off, if you calculate your oxidation numbers, in the +6 state, ends up in the +3 state. Ultimately, this is the +4 state intermediate. Again, I don't expect you to know this particular mechanism or to answer questions regarding it, but I do think it's good to illustrate just where are the different atoms going as this reaction takes place.